So I open the model. We will apply the loads given. So we have to fix this side, the top side, then apply a vertically download the 1000 newtons. So I'm going to fix this side now. So we will start the simulation. We will go to new studies, and I will now here this is a sharp edge. So without the fillet. So here the fillet has been suppressed, so you don't have fillet. So without the fillets, we will model first and see how the stresses are building up. So I'll give a name here, say with the sharp edge. So I'm going to do a static study with the sharp edge. So we will press OK here. Now this side should be fixed. So I will come and fix the geometry this side. And here we have to give a sliding load, 1000 newtons, uniformly distributed over the end face. So how can I give 1000 newtons like this? So we have to apply external load. It's a force. Now if you just select this one, it's going to be a vertically normal load. So I cannot use this method. So I have to go to the selected direction method. Under selected direction method, we have to give the direction to the software. So here face, edge, plane, no direction. So if I want, I can click on this. So click on this edge. Now the direction is actually vertically going up. So I have to reverse that. It should be 1000 meters. So I didn't select the normal method. I selected the select direction method, and I selected this edge. Then I gave 1000 newtons. So you can do it and apply the load also. So I fix this side and apply 1000 newtons. I will save this file because it will sometimes my computer may crash. So I will save my file. Now what we can do is we have to apply some mesh. So make sure the mesh settings is standard mesh and mesh the model with second order tetrahedral elements. So here I'm going to look at the media. I am going to keep the settings in the middle, standard mesh. So we will just apply it and see. So here the default setting is in the middle, and if I enlarge these parameters, it's 4.76. In the slides also it's around 4.76, and mesh tolerance is 0.38. So it's a standard mesh we are going to apply. So I'm going to press OK. So we are going to do a medium level meshing. Press OK. And if you look at the mesh properties, mesh details, mesh quality is now around high quality. I have 6,218 elements, nodes 9,961. This ratio is quite okay. So the mesh is quite okay. So if you just look at these areas, it has correctly modeled. So we will run the solution and see. Now I have told you how to make this decimal number. So we can right click on this, go to edit definitions. And under chart options, we have plot in numbers here, and if you want you can get the maximum value and the minimum value. So you can obviously see that the maximum value appears here, the middle. Minimum value is here. So minimum value somewhere here. So it may be inside here. So maximum value is here. So can I satisfied with this solution? So in the book it's around 80.5. In the slides it's around 79.8 here. So it depends on your computer. So here my value is 79.81. So if you look at the displacements, it's we put it into millimeters. Again, protein numbers here. Millimeters 0.247. So if you try to animate this is the animation. Mind you, this is scaled 45 by 5 times. So that's why you can see a big deformation. Otherwise, it's really a 0.24 displacement difference. So in the stress plot also, if I animate it, you may see this is deviating heavily. But remember, this is scaled up by 45 times. So this is my first answer, 79.8. Can I satisfied with this answer? That's my question. So you cannot satisfied with this answer unless you are very expert on this area. So if you look at the yield value, it's 6,620. So the yield value is very much higher than this value. So this will not fail according to this mesh values. This may not fail, but we cannot guarantee. So we have to refine the mesh and see whether these values are going to increase or whether these values remain the same. So here we don't need to refine the mesh in the entire model because the stresses are higher here. So you need to refine only this area. So I don't need to refine the entire model. Last week we refined the entire model, then we waited a very long time to generate the results. So that's not going to be a feasible solution. So we have to refine the mesh along that sharp edge. So stress concentration is located near the sharp re-entrant edge. We will refine the mesh locally. So this is important. We will refine the mesh locally in that area by applying mesh. So we know problem is here. So we don't need to refine the meshes here. So last week we refined the entire model, which took a lot of time. So we are going to refine only here now and see how it works. So I will right click on this and go to mesh controls. So we are going to control the mesh, apply mesh controls, and this is the edge I am worried about. So we need to select this edge. So when I select the edges, the default element size appears now 2.3. Earlier it was 4.7. Now he has selected the default element size of 2.7 and in that area. So we will accept this one. Earlier it was 4.76, double of that value. And now he has selected 2.38. And the aspect ratio also selected as 1.5. So I will refine this area now. We can click this button called create mesh. Before we do this, we will create a duplicate. So I will create a duplicate, keep the original settings, and I will have mesh control. This element size is now 2.38. So mesh control 2.38 element size. So I'm going to create a duplicate. Characters, invalid characters. I think this mesh control 1. So I created a new study. Loads are same, fixtures are same. So I will come here and apply a mesh control along this edge, and we will create the mesh. So you can see now this area is 4.76. When it comes to the near here, 2.38. The element size is 2.38. Earlier study it was uniform. So I rerun the earlier study. Earlier study should be without the mesh controls. So here they have applied it. I will delete this one. Earlier study it was a normal mesh, standard mesh, this size. This is the earlier results. $79.81. So when I apply the controls, it says now I have applied mesh controls, control 1, control 2. So I don't need to have two controls. I will just delete this and show you how you do it from the beginning again. We'll delete these things. We'll come here and we'll apply a normal mesh first. Normal mesh is like this. Then we can right click and go to mesh controls. Click this edge. This default values I'm going to select, and I'll press create mesh. Now this area is refined. So you can see a control has been applied. Then I can run the simulation. Now you can see the stress value has rise up to 94.2. Earlier it was 79.8. Now it has rise up to 94.2, and the displacement is 0.248. Earlier the displacement was 0.247. So displacement we cannot see a big difference, but in the stressors we can see a huge increase. So we can't believe this value. First result value 79.18 we cannot believe. And we believe this one, the new one. Still we can't believe this one also because it's prime bit. So what we can do is we can further refine the edge. So that's what we are going to do now. Are you okay up to this point? So earlier we applied just a normal mesh, standard sizes. Then I duplicate the model, duplicate the simulation, and applied a control. So the control values are 2.3. Aspect ratio is 1.5. So I created the mesh, and this area you can see mesh details. We have a lot of elements. I have refined it. 99.8 is less than 3 aspect ratio. Then we got some results. That value is 94.2. So we have to, we cannot stop it now. We have to further refine. Still the model is safe under the yield strength, but we cannot guarantee. So we will create another duplicate, another mesh control I'm going to do. So now what we are going to do is, we are going to further refine the mesh. So this we apply. Then we are going to do 3 more studies and apply these kind of element sizes. So the first one is 1.19, 0.6, 0.3. So we are going to get half sizes of the controls. So we come here and we can edit this definition and give a half value here. So it's 1.19. Manually we can type it 1.1. So I gave 1.19 here now under this mesh control. So we can create here even 1.1. Then if I rerun the results, now it takes some time in the computer also. It climbed up to 148. So we started with 79, then 90, 90, 79, around 94. Now it's around 148. So you can see how it's climbing. So started with 79, then apply a control, value is now 94. Then we applied another control, the value is now 140. So it's rising. So we can further refine the mesh and see what's the value. So I will again create a duplicate here. Create a duplicate, then go to controls here and we can edit that value 1.19. I'll give half of this, say something like 0.6. So 0.6 value given. We can do this operation, directly run it. Hmm, 143. I'll see whether the controls have been applied correctly. 0.6 mesh. So now you can see it's very tiny elements in this near this edge. Now it climbs to 188. So are you following me? So we started with the normal setting. We started with the normal setting, just 4.76 element size standard mesh. We got something like 79. Then we applied the mesh control and we started with the element size half of 4.76, 2.38. Then we got a result like this. Then we further refined it to 1.19, 0.6. Now there's another step given in the slides, 0.3. So we can do it and see how the stresses are climbing. So I will do that one also. So I will create another duplicate here. Go to mesh controls here, edit it. This time it's going to create mesh. So this area will be further refined. You can see very tiny elements. We will run the function. Now the value is around again 188. So this should be 0.3. Make sure these values are correctly applied. I have an issue here. It's not saving correctly. Wait, 3. Sometimes your computer memory will not refresh quickly, so make sure you refresh it. So I have an issue here. I will delete all these controls and do it again. I have a small issue here. It's not rising anymore. 188. This value is now again the same value. I will try to apply a control. I will apply a less aspect ratio. This point say 2. See whether you are getting a higher value than this. Here my value is now stopping at this point. But when you have a small mesh, it should go beyond that value. So see whether you are getting that one in your computer. So I will just apply something like a very tiny value, 0.5 to 1.5. So when you further refine the values, the stresses will go up. So it's mentioned in this table. So I started with something like 79, 80. So when I refine the mesh, actually in this one they have reduced the value. Then when you further refine the mesh, it has been increased. So actually it's climbing. The stresses decreases and increases. So here we have to, we cannot guarantee about these results. So we have to have a converge value. So when you further refine the mesh, it will increase. So the problem here is, in theory, we say stress is divergent in sharp edges. So you may have learned in your theory classes that in along the sharp edges, the stresses are very high. So actually, it's infinite. They say it's infinite. So here, since the stresses are divergent in the infinite in the sharp edges, we cannot guarantee our results. So the reason is not that the finite element model is incorrect, but that the finite element model is based on wrong mathematical model. So along these sharp edges, now you can see when I increase, when I further reduce my stress element size, you can see the maximum value is now 1198, which exceeded the yield value. So now what can we say? Whether the model is failing or not. This area will fail. So that's how it works. Now I started with the simple one. Simple result was 79.8. I am very happy that it's not failing. But when I further refine my mesh in this area, stresses are going to increase. Stresses increase. Here it increases to 140. Now when I go here, it increases to 188. When I further refine the stresses model, uh, it went up beyond the yield value. Now it's 1198. Yield is here. Now my model is failing under the same loads. So the theory is correct. Theory says when you have sharp edges, which is zero area actually, this area is actually zero. So when you divide force by area, stresses are coming. When the area is very small, your stresses are very high. So it's going to infinite. So if I can apply a further small size, now this size is now 0.05. So if I go to 0.01 mesh, my results will be obviously higher than this one. So theoretically it says infinite. Here as a numerical value we are getting very high megapascal values. So the theory is actually correct. So we get big numbers here. So if I have a very good computer, I can have very fine measures and prove the theory from the computer simulations. So I hope you understood what I'm trying to say. So when you have sharp edges in these kind of critical areas, now these sharp edges are not really critical because those are not affected by the loads. These are sharp edges. Everywhere we can find sharp edge. But this sharp edge is the most critical sharp edge because according to bending theory, we will get the highest stresses. So we have to make sure this is not going to fail under any load. Say the load is 1000 newtons. It was not failed earlier. Now it's failed. So load is not changed. This is not changed. Only thing I changed was the mesh. So when I refine the mesh, it goes beyond the yield value, and this model is failing. Any questions about this? Now I have to do a change in my model. Otherwise, there will be problems. Now the model has a sharp edge. So we cannot have a sharp edge here. We have to apply a fillet and curve that area. So when you curve that area, you will have more more area than the stressors will not going to be infinite. So I have to have a round edge here. So what we can do is we can, if you go to model now, we have a model with the fillets, but the fillet is now suppressed. So if you enable the fillet here, all these results are going to be affected. Now I can go to this configuration manager here. We didn't do this in the theory class. We can go to configuration manager here and we can have another configuration with the round edge. So the first configuration is with sharp edge. Second configuration is with round edge. So you can have different configurations in the same model. In SolidWorks it's very easy to do, but I didn't do it in the theory class because we didn't have much time. So we can just double click on this and move on to the other round edge model. Now our earlier simulations were based on sharp edge. Now the next simulations are going to be based on round edge. So we can do a study again, new study. Now this time it's based on round edges. So I double click on this and change it to the round edge, and I'm starting a new study. I'm not going to duplicate these things because if I try to duplicate this, I'm trying to duplicate the sharp edges. So we are not going to duplicate sharp edges. We are going to create a new study for round edges. Now same fixture, same loading condition should be applied. So if I want, I can apply them again, or else we can do a shortcut here. We can just drag and drop this fixture to this. Look at my screen. I'm going to drag and drop that fixture to this study. So what happens? This study got that fixture. So I'm going to a previous study and drag and drop this loading condition to here. So you can see it's now copied to this new study. So I didn't do it again. I went to a previous study and I just drag and drop this one, copy into that. This one also I drag and drop. No need to press any control keys, just drag and drop. So why I did that one? Because I cannot duplicate this one. Because if I duplicate this one, this is with sharp edges, this is with round edges. So I cannot duplicate that entire model. I have to create a new study, but I can duplicate this fixture and external loads. What we can do is we can just drag and drop and put it here. So go to previous study which has the settings. Just go and drag and drop here. So these are the shortcuts which reduce your time. Otherwise you have to do it from the beginning. So if you don't follow that shortcut, let me know. So we will now apply a mesh. Now this time also I am going to apply a standard mesh. So it says here we can do that drag and drop here. So they are doing this drag and drop. I'm going to apply a standard mesh. Here we have a 90-degree turn, but I have a fillet also. So these settings I'm going to apply default settings first and see. So default settings have been applied. This curvature has been taken. We will run the simulation and see. Now it says we have to make it floating numbers. $99.47. So now the stressors have been reduced a little bit, 99.47. So can we trust this result? That's my question. Can we trust this result? So we cannot directly trust this result. We have to further refine the mesh. So always remember, don't ever trust the first results coming out of the computer. So we have to further refine the mesh and see what's going on. So how can I further refine the mesh? Now here we have a curve here. So we will create a duplicate first. So I'm going to refine it in this area. So we can move on to the next one. So since we have a curve here, we can apply mesh controls even. But I will go on to the second option called curvature-based mesh. So when I go to curvature-based mesh, the element size is should be given, tolerance should be given, and here it says minimum number of elements in a circle. So if you look at a full circle, how many elements I should have? So here I don't have a full circle, I have a part of a circle. So here we have a quarter circle. So in this quarter circle, how many elements should I place? That's the meaning of this. So these are all done by experience and the calculations. So we have to look at the model size, fillets, radiuses, and give these values. And this is element size growth rate, because we cannot have same size elements everywhere. So the software will have a change in element size. The growth ratio is 1.6. So this is the default value normally. So if you look at my fillet here, it will be how much the fillet radius. So I will go to model. Fillet is 2 millimeters. Fillet radius is 2 millimeters. I will go back to mesh here. Curvature base. So here fillet radius is around 2 millimeters. So we will give the element size around 5 millimeters. Earlier it was given as 4.76. So this element size is now I am giving as 5 millimeters. So this depends on the fillet radius and the size here. So 5 millimeters is given. Then this tolerance is automatically changing depending on this. Then here we can give how many elements per circle. Now this may not clearly understand. You may not understand this one clearly, but if I show you a diagram like this, now this is the thing I am going to give. So I am giving the element size as 5 millimeters here. Then the tolerance minimum element size is 1 millimeters, maximum 5, minimum 1. Then how many elements in a circle? Now if you look at this turn here, this is 90-degree turn. Now if you give 12 here, what will happen? Now it says minimum number of elements in a circle. So if you give 12 here, circle is having 360 degrees. So if you divide 360 degrees by 12, one element size angle is 30 degrees. So I hope you understood that. The element size growth ratio controls the transition between this one. It is recommended that the turn angle does not exceed 30 degrees in sensitive locations where stresses must be correctly modeled. So this is a rule of thumb to remember. It is recommended that the turn angle does not exceed 30 degrees in sensitive locations. So this is the turn angle of elements should not exceed 30 degrees. So if you have a 90-degree corner, you should at least have 3 elements covering that area. So that's the theory here. So I have a 90-degree angle here. I have to have at least 3 elements covering that one. So if you have 3 elements in 90-degree angle, in 360-degree angles, how many elements you should have? It's 12 elements. So for 90 degrees, it should be 3 elements. For 360 degrees, it should be 12 elements. So this is a rule of thumb to remember. Just remember this rule. It's a rule of thumb in SolidWorks. So we have to have 12 here. So I need to have at least 12 elements if you have a full circle. If you have a 90-degree angle, I should have at least 3 elements. So when you model this, you may see 3 elements are appearing here, covering this 90 degree. Okay, so you should have a minimum number of 3. You can have more than 3. If you have less than 3 here, what will happen? Your answers are not going to be correct. So I will apply the mesh and show you how it is coming. Now this area is refined. You should have at least 3. So you can have more than 3 depending on the element size. Now I have 1, 2, 3, 4, 5, 6 actually. So I have more than 3 big ones, 1, 2, 3, 4, 5, 6. So I have 6 elements covering this area, which is good. So minimum is 3. Maximum you can have whatever you like. So I hope you understood what I'm talking about here. Any questions, let me know. So this is given by the failure size here. So that's maximum value. So if you want, you can reduce this value, say to 4. Then this minimum value automatically changes. Normally minimum value is 1/5 of this maximum value. So if you have 5 millimeters, minimum value will be 1 millimeter. If you have 10 millimeters here, minimum value is 2 millimeters. So it's 1/5. So if you want, you can change this also. So 5 millimeters, this is 1. 12 is given depending on the theory. So you will have at least 3 elements here. Here I have more than 3. So if you give 8 here, what will happen? Minimum number of elements in a circle is 8. That is 360 divided by 8. So 45. So you have 2 elements here. So minimum number of elements here will be 2, not 3. So when I mesh it, my element size are getting big. You can see that. Earlier it has 6, around 6. Now I have 3 on. So my answers are not going to be accurate. So you should have as much as possible elements here. So I will have 12. So when you have 12, you can see the mesh is now better than the previous. Any questions up to this? So actually doing simulation is taking a lot of time, not like the modeling. Modeling is actually easier than simulation. So you have to have a lot of experience and you need to know the rules available in SolidWorks, and some experience is needed. So we will run this and see. Now my answer is 120. Red color is here. So earlier it was 99. So it's climbed 120. So what should I believe? Can I believe this result? So that's my question. It's way beyond the yield, way below the yield value, but can I believe this one and produce this part? So we can have a further refine and see whether this is priming or this is converge. So earlier it was 90 something, 99. It's now 120. 99 to 120 is not a big rise. So we can actually do a further refine and see whether this is going to be okay. Converge. Refine to. So how can I further refine this? Easily we can have a small element size that can be done. So I will have say around 3 element size. This is kept as 12. Then we will see a lot of elements are coming. Uh, if you look at, we'll run this stress and see. And then 80. So actually it's now decreased. So earlier it was 99, then it came to 120. Now when I further refine, it's actually staying around 120, or it's actually have a little bit of decrease, 180. So you can see now it has reached to a maximum value and it's now coming down. So when you start to get the lower values coming down, you can see that this 120 will be the maximum value in this exam. So when I have a fillet here, stresses won't go beyond 120. So if I have another refine, it may stay around 118, 117, 16 like that. May not go beyond 120. So you have to have that peak value. You have to reach that peak value, and if you are going down again, that means your peak value is the maximum value you can get under these loads. So I can trust that model now. I can trust this result. 120 I can trust. And I can say that this model is now not going to fail under 1000 meters. 120 is here. So I have applied the fillet and reduced my stresses. Now the model is not going to fail. But if I don't have fillets, like the uh, earlier case, without the fillets, my model will fail. So, any questions about? So you need to understand that when you have critical areas, you need to apply these round corners, chamfers, fillets, or you need to apply more thickness to that one, or you have to apply different material here. So you cannot apply different material because it's a single part. But if you have two body parts, you can apply different material here and make it strength. So I hope you understood what I'm doing. Any questions about this? Let me know. Resume my session. So I will not give a break here because I started late. So we will move on to the next topic if you don't have questions. So remember when you have sharp edges, don't have sharp edges in critical areas. So you need to always have fillets on in these areas, and don't ever trust the first simulation results. Do several simulations and get the optimum value. So always try to get a converge solution. That's the whole point of uh, whole point you need to remember. I will move on to the next example. So from the examples here, I'm going to teach you the theory. So that's how the simulation class goes on. So we have to do some simulations and check the theory in SolidWorks. So now this is about another static analysis of a link. So the link model is like this. So I have to apply some pin supports here. Earlier we just applied some fixed supports. Now this time it's pin. We need to calculate displacement and stresses of the link shown in figure 5.1. The link supported by tight fitting pins in the two end holes, and it is loaded by a loose fitting pin at the central hole with a force of 30,000 Newton. The two holes are not loaded. Two other holes these are not loaded. Open the part file and we do that. And the material is chrome stainless steel. So we are going to look at a special boundary condition called symmetric boundary condition in this model. How to prevent the rigid body motions and limitations of small displacement T. So now if I open this file, now this is the full design. You can see that this design you can analyze as a whole, or you can analyze only half of the design. So that's what they have done here. We don't need to analyze the full design. We can analyze only half of the design and get the calculations quickly done. So to simulate a pin support that allows the link to rotate above the pin axial, radial displacement need to be restrained and circumference displacement are. So what do you mean by this? We will discuss quickly. So there's a theory behind here to simulate a pin support. So pin support is this one that allows the link to rotate above the pin axis. So it should rotate like this. Radial displacement need to be restrained. Radial displacement are the displacement go along the radius. So it should not displace radially, and circumferential displacements are allowed. So these kind of displacements are allowed, but not the radial displacement. So you need to give that under pin supports. Furthermore, displacement in the axial direction need to be restrained in order to avoid any rigid body motions of the entire model. So displacement along this axis also should be restrained. So we will look at how to do this model now. Now here we don't need to apply the get the entire model. We can go to configurations here. Under configurations, they have given us the half model. So we can only analyze a half module, which is going to be easy. So because it's symmetric, so I can go to new studies, get the static study. Say I will say half module. Now we have to fix this part. So this is a pin support. So if I come here and now the material is chrome stainless steel. So we will come here and fix this. So if you just directly go to fix geometry, you will get this one. So I don't need to fix the entire thing. So that's not my point. I have to go and select this kind of a hinge support. So you can see how the hinge support works. The hinge support allows me to rotate this, acting this as a hinge. So when you click on this face, now it will allow my model to rotate along the pin, but it will not move radially radially or it will not move axially. Only circumferentially it will move. So the hinge support can be given, or else there's another way of giving this. So I will give the hinge support, or else you can say suppress this and give another support, like go to advanced features, and we can select this kind of a method on cylindrical faces. You can see this kind of a thing we can give. So we have to stop that axial movement. We have to stop the radial movements expanding. We can allow circumferential. So when you click on this, we have to give those conditions. So I will come here. So you may understand it now clearly. So we cannot allow radial movements. That is, we cannot allow this to be expanded. This hole should not expand. And we cannot allow this expansion. So you have to give 0 millimeter. So what is the meaning of this? I am not allowing this to increase its radius. So radius will not will change. It's 0 millimeter. But I will allow this to rotate. Circumferential movements are given. And the last one is I will not allow axial movements. So the meaning of this one is I will not allow radial changes. I will not allow axial movements. I will allow circumferential turns. So if you give here 1 millimeter, what is the idea of that? I will allow 1 millimeter change only in axial direction. So I will allow 1 millimeter change in radius. That's my condition. If I give 0, I will not allow any change in radius. I will not allow any change in axial direction. So it should not move axially, should not expand this hole radially, but it can rotate circumferentially. So these are the conditions we are given. So the hinge support is actually easy. Hinge support will take care of all these things. Or else you can give this kind of a cylindrical base. So either of these two will work. You don't need to have both conditions given. It's over-defining. I don't need to give over-defined conditions. Just give a fixed hinge support or a cylindrical. I hope you understood how it has been given. Any questions? Let me know. Next, I will apply symmetric conditions. Now, try to give symmetric conditions to these two faces. So how can I give it in SolidWorks? So I have given this pin support here. Then we can give it in different ways. So I have showed two ways of giving it, and we have to give a symmetric condition like this. So I will expand this. So symmetric condition should be given. So it's under advanced features, fixtures. We have the first condition, symmetric condition. So I can select this face and this face. So when I select these two faces, automatically uh, it will model the, sorry, these are the two faces to get symmetric. This is the plane which has to be selected. So along this plane, now if you look at my model, so it should be parallel to this right plane. So if I press OK, at least one displacement component. So it should not displace normal to this. So you have to give this one also. So these are the conditions we should give. So we have to select the symmetric plane, symmetric conditions, and select these two faces, and select a plane which is 90 degrees to this symmetric condition. So I'm saying that normal to plane, there is no movement around normal to plane. So when you press OK, it should simulate the other area. So remember that how I did it. I went to the advanced fixtures, went to symmetricity, symmetric condition, selected these two faces, and this should be symmetric about this plane. So I selected that plane, and zero value is given here. There is no movement along normal to that plane. So I hope you are okay with this. Now I have to apply an external load. So the loads are applied like this. So I should apply half of the load. Earlier the model has 30,000 load, 30,000 Newton for the entire model. Now I am getting half of that. Half of the value is 15,000 newtons. So I will give 15,000 newtons to this. So how can I give a vertically down load 15,000 newtons? How can I give it in SolidWorks? So we have to give 15,000 here, normal to this face. So they have given normal to plane. So now we cannot give normal to face. We have to give normal to plane. So how can I give it? So we will go to forces here. Now you can see the boundaries have been splitted. So we have learned the splitting theory. So this can be selected separately. So they have splitted the boundaries. Now if you just select this one, it's not the correct value. It should be going vertically going down. 30,000 is given, but I cannot select normal. So I have to select a direction method. Select direction method and select a direction. Say direction maybe we will select a plane. That is the easiest way. So normal to this plane. So normal to this plane, you can select this one and give 30%. And we have to release this. So I hope you understood how I gave it. If I just give normal direction, it will be normal to this face. So it should not be normal to face, it should be normal to the plane. So I selected the plane from this one. So you can always go expand this area, minimize this area this way, and select the plane here, top plane, and normal to plane is 30,000. So that's how we get. You can give it and see. Okay. Then we will apply the mesh. So I have given the loading. I hope everyone understood this. Then forces given. Then we have to apply a mesh. So in this book they have given uh, high quality mesh. So curvature-based mesh was given. So or you can go to standard mesh and select the fine values. So we will give it and see element size. Always will have this one and curvature-based mesh. So this will be given just normal settings. Okay. Now I can look at the mesh details. Element size is given 7.83. Then we have 9,745 elements. Uh, Total not this much, 99.8 is less than 3, so quite okay, means is quite okay. Then we can run the simulation. So results obtained, maximum value is 334, which is beyond the yield value. So this model will actually fail under this condition, may fail. So minimum value is okay, but the maximum value it will fail. So if you try to animate this is the situation. So if I try to have try to have a one-to-one scale, you won't see a big deflection, but it will fail in this area. So maximum value will exceed the yield value. So we don't need to actually rerun the things and see. So you don't need to actually refine the mesh. It's no point of refining the mesh. Even in these mesh conditions, it will fail. But if I just look at the mesh now, 7 point something. Say I will just go to a standard mesh and try to do it. Now this is the standard mesh. Earlier it was a curvature-based mesh. I will run it and see. It's still 331. So no point of actually refining the mesh further. It's failing in this area. So you have to do something about this. otherwise the model will fail from this side. So if you just look at the full model, so if we can do the same thing for the full model and see whether we are getting the same results. Now we did for the half model using symmetric conditions. I will do the same one for the full model. So we will go back to full model. Then create a new study. This is for the full model. Now I cannot duplicate because the boundary conditions are different. So you can duplicate external loads also, you can't duplicate. Fixtures you can duplicate, but I have two fixtures at the moment. So you try to duplicate one fixture from this, we can duplicate only one, and this one I have to do again. So I will try to duplicate this cylindrical one here, but this side also I have to do it. So I will again add the fixture here, advanced fixture on cylindrical faces, this cylindrical face. Then radial motion should be removed, not allowed. Circumferential we allow, and axial we don't allow. So we should not allow axial and radial. Then we have to apply load. It should be normal to select a direction. Direction is easily we can take it from the model. The normal to top plane, and it should be normal 30,000. Earlier I gave 15,000. Now full model I have to give 30,000. Okay. So I have to select the bases. So the base is this. So the direction should reverse. So I hope you understood how we give the pin support on cylindrical, and load is normal to the plane. We can apply a mesh, normal mesh, standard one. And right click and create the mesh, run the mesh. So the maximum value is 169. So yield value is 172. Now this time we may think that this is not failing, but we have to apply a fine mesh and see. whether this is going to fail. So I hope you understood how this works now. If you want, you can have a finer mesh. Don't satisfy only on one value. If it is yes, if you're going beyond the yield value, definitely it's failing. So if you are not getting that, if you are in the safe margin, refine the mesh and see whether you are going to be failed or not. So I will apply a curvature-based mesh. Uh, Minimum value we will say around 5 and okay. So it's going closer to the yield value. So better you treat this as a failing model. So when you increase the increase the elements number of elements, this area is high, have a high probability of failing. So if you want, you can refine this area and check again. So I hope you understood how this is done. So you can do the modeling for a half model or a full model. Full model will take some time to mesh and will take some time to give the answers, but the half model will give the answers quickly. Any questions about this part? So last time I showed you how to get a report about this analysis. Now if I want to get a static full model report, you just click on this report tool. It will automatically create a report for you. So you don't need to worry about creating the reports manually. So I can just include this information and on the report and press apply. Sorry. And press publish. So software has generated the report for you. So you can see all the information given here. Fresh information given. Loading. Then the simulation results. But the conclusion is not given. So this is the most difficult part. As I told you last week, you have to write your own conclusion. So this is the difficult part. So that's why we have to learn the mechanics and the other theory related to static analysis. So then write the conclusion why there is a problem like this. What can I do to recover this problem? So what can we do? That is the most difficult thing to write. So any questions up to this point? So I'm introducing new options one by one using models. Any problems, let me know before I go to the new one. So I will look at the next model. It's about static analysis of a hanger. So we have we have an assembly file now. So in the theory modeling class, I didn't go through the assembly modeling because I didn't have much time. So now here we will use the assembly model given in the book. So this is the model. We have three parts. This is the fixed supports. This is fixed to a wall or something like that. Then we have two parts like this, and we apply a 1000 Newton load to this. So what happens when I apply 1000 newtons to this model? We will see what happens. So I have given you a folder and we have three parts here and one assembly part. So these are the three parts separately designed, and the assembly file is given separately. So you need to have everything in a single folder. And I'm going to open the assembly file. Now, if you look at this one, this is assembly file. Hanger is the full assembly file, and we have this support hanger 1, hanger 2, and hanger 3. So we are going to apply 1000 newtons to this thing and see what happens to the motor. So I will run the static analysis. Now you can see a new area has been deployed now. So it says component contacts global contact bond. So this was not available in the earlier part files, earlier single files. Now we have assembly. Automatically software has created this setting for you. What is the meaning of this setting is, we will treat this entire assembly as a single part, bonded. That is, these areas are bonded together. There will be no penetration, there will be no sliding between the joints. So here this part and this part is perfectly bonded. This part and this part perfectly bonded. Perfectly bonded. So if you look at our theory, there are conditions like bonded, no penetration, then allow penetration. So those kind of conditions can be given. The measure will bond common areas of the selected components at their interface with all the other components. This option is available for structural, static, nonlinear frequency, buckling, and thermal studies. This contact condition comes with two options: compatible mesh and incompatible mesh. So you can see bonded is the we are assuming it's a perfect bonded area. So this is perfectly bonded, perfectly bonded, perfectly bonded. So that's the assumption we are taking here. But if you want, you can assume this is penetrating, allow penetration, likewise no penetration. So those conditions we will later observe what happens there. So first we will now if you just right click on these things, you can go to these areas called contact sets. No penetration is given, bonded is given. So we can change these things to different areas. So we will look at that later. For the time being, just apply this as a global condition, global contact bonded condition. Now I will rename this as bonded. And we will fix now. This area is fixed. Then I'm going to apply 1000 newtons to this area. So I am in the global bonded condition. I have fixed this area and I applied 1000 newtons. So we will apply a force of 1000 newton to this area, normal to the. Now here we are not talking about mesh controlling. We have done mesh controlling earlier also. So we will take default mesh conditions and get us result. So if you just run this directly, software will put the default mesh conditions and give you a value. So we got this result now. If you look at our displacements, point 363. So if I run this as an animation, this is the bending happen. So these areas are perfectly fitted. Perfectly fitted. It's acting as a single part. So if you do a welding design, your welding is perfect welding, perfect welding. So otherwise, if you put some glue or if you revert these areas, it's a perfect bond, perfect joint. So it's coming from this global condition, global contact bonded condition. Any questions up to this point? Now, if you look at the stresses, it may go beyond the yield value we see. Now the yield value is 206. This is less than yield value 106. So we may think this is not going to fail, but we have to refine the mesh and see. So it may not fail, but we cannot guarantee. So we are not going to refine the measures now. We have done that earlier in other examples. So we will look at these conditions now. So the objective of this lesson is to look at how the assembly files are going to be analyzed. So now the global condition is given as bonded. Now the next one is I'm going to assume this is not going to be global bonded. We are allowing some penetration. So the next condition is we allow some penetration here. So in this area. So how can I give that in SolidWorks? So we can allow the software to act this area, local area, as a normal, say, allow. There's a method called allow penetration. So we can ask the software to have some penetration here. So we will do that now. So we can right click on this one and go to this tool called contact sets. So I'm going to select this one and apply a allow penetration condition to this area. This area is bonded, this area is bonded. But when you apply some loads, what happens normally? This area tries to penetrate or tries to slide along this. So that's the normal situation. So these will not be affected so much. This is the point which we will get a lot of stresses. So we will try to model it accurately. So we can go to contact sets here, and there's a tool called allow penetration in this area. So now I have to select this face, and there's another face here. I cannot select it. So there's a problem of selecting. So there's a way of doing that in SolidWorks. Uh, we have to get this exploded views. So this theory also I didn't do with you. So you can explore this model. So we will explore this model and try to get it. We will go to explore the status. So it is somewhat slow. So when I explore, this is the exploded view. So I will go back to the model. Now the exploded view is shown. So you have to go to models here and go to these configurations and right click and explode. If you want, you can collapse it, or right click and explode. Why I exploded is I have to select this face. So this theory also I didn't do with you because I don't have much time left in the subject. So static bonded, I will go to this area again. Now I will create a duplicate of this and have allow penetration. Allow penetration. So I created a duplicate. Then right click on this, get contact sets. Please wait for a moment. Get the allow penetration condition. Click on this face and this. So what I did was I allowed the penetration. So don't have this in the same box. You have to put it in the other box. So here what I did was I allowed some penetration here. You see this allow penetration. These areas are still bonded. Even though this is exploded view, it's not actually exploded. It's just for the visualization. So I allowed it. So that's what I did. And now you can apply a mesh and run the results. So if you look at this one now, I have allow some local penetration. These global areas are still bonded. So I have overwritten right here, overwritten here as allow penetration. So you run this and see the results. Now my stresses, what are my stresses? 368 now. So now clearly it's going beyond the yield value, 361, 68. So if I just go to edit definitions and mark the maximum area, maximum area is now here. So it's obvious, maximum area is here. Earlier, when I asked to be perfectly bonded, what is the maximum area? Where is the maximum area? It's 107. I said that this model will not fail. But you can see when I change the conditions, how it's drastically changed my outputs. Now, maximum value. Earlier the maximum value is here. Now the maximum value moves to here because I allow the penetration here. So now what can I say? Model is failing. So you can see depending on the boundary conditions, how the results are changing. Depending on the mesh, how the results are changing. So it's very difficult. Simulation is not an easy thing. So you have to apply correct boundary conditions. And you can see now this is penetrating. This is penetrating, this is tend to bend more. That's why you are getting lot of stresses here. Earlier stresses were here, bended from here. Now it's bending from here because it's allowing penetration from here. So when I animate this, you can clearly see what happens. So it's penetrating. And if you look at the displacement values are much more higher than earlier. It was 5.13 now, it is 5.13 now. Earlier it was very little, little displacement, 0.3. Maximum here earlier. So I will just apply maximum pump. Maximum is here. Max is here. Now the max is where? Max is here. Sorry, max is there again, but the value is much more higher. Any questions about this? Now I have overwritten the global condition. Here the bonded condition is still there, bonded condition is still there. Here I have overwritten this one by right clicking and allowing some penetration. So we selected this face and this face. So you have to go to this exploded views and select the faces correct. So we will look at how to apply allow penetration condition. Now no penetration condition. I gave allow penetration, but we can ask the software no penetration. And then what happens when you apply no penetration? It may try to slide along this. So we will duplicate this and say next one is no penetration. Now I'm going to change my conditions here. Run the contact sets. This is a contact set. So we will try to edit this definition to no penetration. So the same conditions given, same phases. I can apply a friction if I want. I say this is not going to penetrate, but if it's not bonded, then what happens? It will try to slide. It will not penetrate, it will try to slide here. So we will see after we run the simulation. Now what happens here is, now if you look at the model correctly, you can see it has been slided. So when you animate this, you can see it's sliding. It's not penetrating at the moment, it's sliding. So due to this loading condition, it's sliding. And the stressors are now reduced a little bit. Earlier it was 300 something. Earlier it was 368, so it's failing. Now it's reduced to 189. So when I get the maximum values, maximum value is still coming, but now the maximum value is in the top side. Earlier the maximum value was in the bottom side. So you can see when I change my conditions, how the simulation result changes. So it's really important to give the correct boundary conditions, correct loading, correct materials, those things. So the geometry is not really not really important compared to those conditions. Geometry is important, but the boundary conditions are really important. How you give the boundary conditions are really important in SolidWorks. So I hope you understood this how to do a simulation in an assembly. So we took a simple assembly and we considered everything as bonded earlier. Then we change these conditions here to allow penetration and no penetration. Any questions about this? Just go through my slides and see how I have done it. All the information is given. So, any questions before I wind it up? So we will finish the class early today. So next day I'm going to look at some more modules and try to analyze static analysis further in SolidWorks. Then we have to start uh, fluid flow simulations in SolidWorks also. So if you have any questions related to things I did, please inform Ms. Chaturika, that she will inform you. Always directly contact me and let me know what are the questions you have. So basic thing is you have to do these things and check, run the simulations, do the designs and get used to the software. That is the only way of getting through this. So I hope you understood the content I did today. So we will meet next day. Thank you.